So I'm thrilled to welcome Amy Unruh here with me. She's going to talk about machine learning operations on Google Cloud platforms. Amy is a developer relations engineer for the Google Cloud Platform, where she focuses on machine learning and data analytics. She has a PhD in computer science and AI, and has worked at a variety of research and development labs and startups, and has written a book on App Engine. Today, she will talk about machine learning operations on Google Cloud Platform, and I'm really looking forward to this one. So Amy, the stage is yours. Please start your presentation, and if you have any questions, use the Q&A and ask your questions there. Thank you.
So, hi, I'm Amy, and as you just heard, I work at Google on machine learning with a particular focus on the new Vertex AI products. So in this session, I'll first talk about why productionizing ML is hard and discuss some MLOps design patterns that can help. And then I'll introduce the newly launched Vertex AI platform and talk about its support for MLOps. Then I'll do a deeper dive into something called Vertex Pipelines, part of Vertex AI, and show a demo. And then finally, I'll briefly introduce two more Vertex AI products, model monitoring and the feature store. So building the first proof of concept version of a machine learning system is usually pretty straightforward. But when you try to productionize and scale out, typically what was built as the prototype is only a small piece of what you need to pay attention to. And it can be hard to scale out and keep your system operating continuously. And I should add that here I'm using productionize to indicate making the system more robust. It doesn't necessarily need to be external facing. So many of you have probably seen a graphic like this before. I like it a lot. This is the common perception when thinking about a machine learning application. Many of us anticipate that the main challenge is going to be just getting the models working properly and accurately. But the reality is that building the model is only a small part of what you need to be paying attention to. So why do things become so much harder when moving to production? So here's an incomplete list of some of the reasons. And these are things we hear from customers too. So first, data cleaning and processing becomes very hard at scale. Here, some people say that it's like 90% of their overall effort. Dealing with data, getting it to where it needs to be, feature engineering, et cetera, is really a large part of what you need to do to put a machine learning system into production. It can also be hard to scale out training and serving infrastructure to make sure that your system has sufficient resources when it needs them and that it can scale back down when they're not required. Another set of problems can come up from issues like model or data drift or training serving skew. So your production infrastructure needs to be able to detect and handle situations where a model is no longer sufficiently accurate, or new data might indicate that model retraining is necessary, or online prediction data is not consistent with the feature engineering that you did for model training. And of course, in a production environment, access control and security become much more important, and lots more that I won't talk about. And so we have this growing discipline of MLOps. The term has really just come into common use in the last couple of years. And it has the goal of unifying machine learning system development and operations. So to guide teams through the challenges of doing production machine learning. It takes both its name and some of its core principles and tooling from DevOps. However, it has its own challenges. For example, it's necessary to manage the lifecycle of data and models as well as code. And that has led MLOps to evolve as a domain of its own. So let's look at some MLOps patterns and practices that can help address some of the problems I showed. So here's a high level and incomplete list. First, formalize your ML workflows. For production, move away from stitched together notebooks or monolithic scripts. And equally important, your ML workflows should behave in the same way across environments. Workflow execution should also scale out resources when needed and scale down when they're not. Designing for composability, modularity, and reuse of ML workflow building blocks will ensure that you can reliably reproduce and run your workflows. And similarly, your infrastructure should support workflow monitoring, versioning, and caching. And this typically requires making ML workflow metadata explicit. The data scientists on your team will probably be prototyping in notebooks. And so you also need some well-defined processes to capture that work and move it out of notebooks for production use. And mechanisms for supporting collaboration and role-based access control also become important. Informal methods of providing team members access just won't scale anymore. So that was a helpful list, but how to operationalize these patterns and actually use them. So that's the focus of the rest of this talk. A typical machine learning workflow might look like the one on this slide, with experimentation and prototyping stages, as well as automation of training, model evaluation and deployment, and monitoring and retraining. So you can see that there are many steps and actions that need to be coordinated. And there are particular capabilities that need to be supported, like model monitoring for one. And you can see that in a production environment, it won't work for this to be ad hoc. So by formalizing and orchestrating these workflow steps, we can automate, track, and reproduce workflows. We can more easily debug problems, and we can reuse some parts of a workflow elsewhere. So let me now introduce Vertex AI, which we have recently launched as part of Google Cloud. Vertex AI is a managed machine learning platform to speed the rate of experimentation and productionizing of machine learning models. Vertex AI provides a suite of products for each stage of a machine learning workflow, running the gamut from gathering data to feature engineering to building models, and finally deploying and monitoring those models. As part of Vertex AI, a suite of MLOps products has been released in preview, which is like beta. So this includes not only Vertex pipelines, but a feature store, model monitoring, a managed metadata server, support for running experiments, and more. So in this talk, I'll focus on the most detail on Vertex pipelines and also briefly introduce model monitoring and the feature store. So as we saw with that graphic of a canonical ML workflow, formalizing orchestration is key to being able to productionize such a workflow. A pipelines framework is the backbone of production ML systems. And so Vertex pipelines is a key part of the Vertex AI story. So next I'll introduce Vertex pipelines in a bit more detail, talk about how it's related to the open source Kubeflow Pipelines project, which some of you might be familiar with, and then show a demo. And then I'll circle back to some of the design patterns I mentioned and discuss how Vertex pipelines and Kubeflow pipelines helps to operationalize them. Vertex pipelines is serverless. So that means that you don't need to deal with managing an underlying cluster infrastructure. It scales up when you need it to, and you pay only for what you use. So it lets you just focus on building your pipelines. Vertex Pipelines has data scientist-friendly Python SDKs that make it easy to define and run pipelines and prototype them. With the Vertex Pipelines SDKs, you can use pre-built components, or it is also straightforward to define your own custom components. By components, I mean pipeline steps. So you can add control flow to your pipelines, and the SDKs make it easy to experiment and prototype right from notebooks. Vertex Pipelines has a metadata layer to simplify the process of tracking artifacts generated throughout your machine learning workflow. So information about artifacts, lineage, and execution information is all automatically logged to this metadata server when you run a pipeline. And then you can explore the results in the UI. And if you like, you can also query the underlying metadata server directly, which lets you do things like compare run information, group artifacts by projects to track usage of data sets, et cetera, and just do general analysis. Vertex Pipelines has support for Google Cloud Platform's standard enterprise security controls as well. So that's things like identity and access management and VPC service controls. So let me say a little bit more about the Vertex Pipelines SDKs. It supports 2 open source Python SDKs, KFP, Kubeflow Pipelines, and TFX, TensorFlow Extended. So you can use both of these SDKs with both Vertex pipelines and open source Kubeflow pipelines. I'll say a bit more about that in a second. And in the examples I'll show for this talk, I'll be using the KFP SDK. So you need to use KFP version 2, which has a separate namespace in the SDK to define Vertex pipelines. And you'll see this in the demos. To run version 2 pipelines on an open source KFP installation, you need to use the so-called V2 compatibility mode. So that allows you to run the same V2 pipelines on both platforms. There are some aspects, like as I speak today, there are some aspects of this compatibility mode that aren't quite working, but will be fixed very soon. So it works for some pipelines and not others, but check back in a week or so and it should be solid. So some of you may be wondering how Vertex pipelines relates to Kubeflow pipelines. So first there's the Kubeflow, First, there's the Kubeflow open source project, which has a goal of making deployments of machine learning workflows on Kubernetes simple, portable, and scalable. So you may be familiar with that project. It has multiple components, and Kubeflow Pipelines is one of them. Then, from the Google Cloud Console, you can install a hosted version of just the Kubeflow Pipelines part of Kubeflow. So this installation runs on a GKE cluster, where GKE is Google's hosted Kubernetes. And now there's Vertex Pipelines, also access to the Google Cloud Console. It's fully managed and serverless. And as I mentioned in the previous slide, it supports the same SDKs as does open source Kubeflow pipelines. So this means that pipelines you write using those SDKs can run on both Vertex AI and on an open source installation, which is pretty cool. All right, so now I'll switch to some demos and as part of that, show some pipeline code. So I decided to err on the side of caution and pre-record my demo, which hopefully will all work smoothly. And a link to the example notebook I'm using in the demo is in the resources slide at the end of my talk. Okay, so I'll play the demo now.
Let's take a look at a pipeline run in the UI. Then in a notebook, we'll look at the code that produced it. Then we'll walk through modifying the pipeline code and submitting a new run that includes the changes. And as we do this, we'll show how pipeline step caching makes iterative development easy. So from the Cloud Console, I first navigated to Vertex AI. Then I clicked on Pipelines in the left nav. Here's a list of my pipeline runs. This example pipeline uses the Vertex AI AutoML service, where you can bring your own data to train a model. For this example, I'm training a classification model on tabular data. While the details are not important to this demo, the model is learning to predict whether a given comment on a video is spam or not. So this pipeline is creating a data set from the comments data, training a model using that data set, then getting evaluation information about the trained model, rendering some metrics visualization, and then using the eval info to decide whether the new model is accurate enough to deploy. If the model is sufficiently accurate, then the deployment step is executed. This is done using the Kubeflow Pipeline SDK's support for conditionals. Let's examine the pipeline's UI in a bit more detail. For each step in this pipeline, you can view its logs. You can also view information about the step executions and artifacts. This information is automatically logged to an underlying metadata server. And in a few minutes, we'll look at how we can query the metadata server directly and use this information to compare results across runs. So we can look at the details of an artifact, and we can see which artifacts are produced and consumed by which pipeline steps. We can also view the lineage tracking for the artifacts. So this tracks how the artifacts are connected by step executions. It's kind of the inverse of the view that we just had of the pipeline step executions. Here we're focusing on the artifacts, things like models and datasets, connected by the executions. The tracking information shown is not necessarily just for a single pipeline run, but for any pipeline execution that has used a given artifact. Most of the pipeline steps in this example are defined using a set of pre-built components for accessing Vertex AI services, things like dataset creation, model training, and deployment for serving. In addition, I'm using one custom component to extract and render the metrics information and visualizations that you saw in the UI. So I'll show the code for this pipeline shortly. What if we want to compare the results of two runs? We can do this from the UI by selecting the runs we're interested in and clicking Compare. You can see that information about the run parameters and generated metrics for all the selected runs gets aggregated there in the right-hand side panel. We could also directly query the metadata server. That's where information about the pipeline executions and artifacts gets automatically logged, and compare run information that way. So we'll look at how to do that shortly. Next, we'll take a look at how this pipeline is defined. Both SDKs make it easy to define and run Vertex pipelines right from a notebook. For this example, we'll be using the KFP SDK. I've already done the initial notebook setup, so I'll skip right to the pipeline code. First, I'll do some imports. Then, I'm defining one custom component. It grabs evaluation information for the trained model and uses that to determine whether the model is accurate enough to deploy. It also renders model metrics information. You might remember seeing that in the UI. I'm defining a Python function-based component. So I define a Python function that implements the pipeline step that I want and add a component decorator. When I evaluate the function, the component is compiled to what is essentially a task factory function that we can use in the pipeline definition. This pipeline component includes in its inputs an artifact of type model and outputs two metrics artifacts as well as a string. And as we'll see, these outputs can be consumed by downstream pipeline components. As part of the compilation process, a component YAML file is generated. While I won't have time to show it here, you can share the YAML component definition with others. You can put it under version control and use it later to create the pipeline step in another context. The other pipeline components in this pipeline are drawn from a set of pre-built components, Google Cloud Pipeline components, that let you interact with Vertex AI and other Google Cloud services. I'm using these components for the rest of the pipeline steps to create a dataset, train and upload a model, and then conditionally deploy it. Then here you can see I'm using the custom component I just defined for the model eval step. You can see that one of its inputs is the model output from the training step, and that the conditional expression uses one of the outputs of the model eval step to decide whether or not to deploy the model. So now I'm ready to evaluate the pipeline definition and compile it. Then I'll create a pipeline client object and submit the Vertex pipeline run. I can click on the generated link to view the running pipeline in the console. I can also query the information logged by the underlying metadata server directly using the Vertex AI SDK.
Okay, I'm relieved that demo played successfully. So back to this question. How can Vertex pipelines or Kubeflow pipelines play a part in operationalizing helpful MLOps design patterns and practices? So you remember this list I showed earlier. Let's walk through some of the ways that a pipelines framework helps. While I'm focusing mostly on Vertex pipelines, these points hold for Kubeflow pipelines as well. So of course, pipelines helps you formalize your ML workflows. That's a primary goal, of course. Let's look at these, some of these other patterns as well. An ML workflow should be reproducible and portable so that it runs the same if it's rerun or in different environments. Pipeline steps are container-based so that they will run the same anywhere. And as I mentioned, the KFP v2 SDK allows a pipeline to be run both on Vertex AI pipelines and an open source Kubeflow Pipelines installation. It's straightforward to clone a pipeline and run it again, and step-level caching is supported as well, as you just saw in the demo. This makes it easy to experiment with pipeline variants or to debug a step. Support for modular design and composable pipeline building blocks is also important, so that the pipeline steps can be essentially plug and play. It supports easier debugging and can be reused and shared. The KFP SDK allows users to share components, that is specification of pipeline steps, as well as pipeline definitions. Components can be compiled to YAML format, as you saw in the demo, put under version control, and then later loaded from their source URLs. I didn't show that last part in the demo, but it's very straightforward as well. The Pipelines SDKs also make it easy to create pipeline components without needing to directly use Docker, and make it easy to prototype in a notebook, as was hopefully one takeaway from that demo. So given that pipeline components are composable and reusable, a next step is to provide pre-built building blocks to guide the construction of canonical ML workflows, and of course, reduce the effort required to build pipelines from scratch. So in the demo, I used a set of pre-built Google Cloud pipeline components to train, upload, and deploy a model to Vertex AI. And the TFX project also provides a number of similar such components and libraries too. And in addition, pipeline steps can call out to any service or essentially implement any functionality that can be containerized. So we can provide pre-built components that wrap any machine learning or related services. For example, on Google Cloud, things like data flow. There are many such in the KFP repo, and more are being added all the time. Explicit use of pipeline metadata is another key to effective MLOps. So once we can treat workflow artifacts, things like models and data sets, as first-class citizens with defined schemas, then we can automatically track and reason about their use. So both Vertex and Cubeflow pipelines automatically log to a metadata server during pipeline execution. And in the demo I showed, you could see this in the UI. And so this in turn enables automatic lineage tracking and supports features like reliable reproduction of previous pipeline runs and comparison across runs. So here's a summary of some of the Vertex pipeline features, many of which you just saw demoed. Has easy to use Python SDKs, which make it straightforward to prototype pipelines and then move them to production. Vertex Pipelines is serverless and scales automatically when you need it to. So you never need to worry about managing and provisioning an underlying cluster, and you just pay for what you use. It automatically logs and tracks metadata and lineage information, and it provides support for GCP's standard enterprise security controls. So things like identity and access management and customer managed encryption keys. So next, I'm going to quickly introduce two other parts of Vertex AI that also fall under the umbrella of the MLOps story: model monitoring and the feature store. So let's return to this canonical ML workflow. Once you're happy with the model and deploy it, you're not done. You need to monitor its performance to detect if over time its predictions are becoming less accurate, which almost always happens. So this is where Vertex model monitoring comes into the picture. Model monitoring alerts you when model performance changes. You set it up to monitor a particular deployed model. So you set it up for any number of models that you've deployed. And it currently looks for two classes of changes. The first is training serving skew. So this can occur when the feature data distribution in production is different from the distribution of feature data that was used to train the model. And this can be a strong signal that the performance of the model may be deteriorating. And it can also be an indication that you're inadvertently doing feature processing for prediction differently than you did for training, which I'll talk a bit more about shortly. The model monitoring service also detects prediction drift. And that's when the feature data distribution in production is changing significantly over time. So once you're alerted, the monitoring information can help you identify the cause for the deviation, which can trigger retraining or tuning of your model. Finally, let me briefly introduce the Vertex feature store. An important part of a machine learning workflow is feature engineering. And part of that is ensuring that you're doing feature processing in the same way for training and serving. But it's hard to share derived features with others, others on your team or across teams in a company. And it's hard to build infrastructure to do this properly at scale. So the Vertex feature store provides a fully managed store that lets you discover, query for, and share derived features and serve them at scale and with low latency. So use of a feature store helps to reduce effort. Different teams aren't replicating each other's work, and it helps to alleviate training serving skew. You can compute a feature once and use it for both training and serving, and know that you're using a feature that was computed consistently in both contexts. So one interesting and useful aspect of how the feature store works is its support for point-in-time lookup. And the idea with this is that if you have timestamped training instances, you want to fetch and use the most recent derived features that were created prior to the training instance's timestamp. So that is, you don't want to use features derived at a later date from the training instance, as that can cause data leakage. So the Vertex feature store handles this and will automatically fetch the features for the right point in time. And I don't have time to go into more detail now, but there's a linked blog post that provides a bit more information, and the documentation does as well. Okay, so let me wrap up with some resources for learning more about Vertex pipelines and the rest of Vertex AI. So there's a link to the example notebook I showed, or rather, it's not exactly the same example. It turned out that I needed to use a different data set, but it's essentially the same code. And see the link to the slides in the lower right-hand corner. So if you grab the slides, you can get all the links from there. All right, thank you very much.
Thank you so much, Amy. Super interesting. So we are going to share your slides so anyone who attends Craft can check out the links and watch the presentation again. So I'm looking for the questions part. No questions so far. So if you have any questions to Amy, you can have a chance to ask. But until we are waiting for the questions, if there will be any, I would like to thank you so much for the presentation. This is going to be mailed to you. This is a mug with your image on it. So I hope you like it. Nice. It's a nice...
I hope that wouldn't be too scary a thing to see first thing in the morning.
Yeah. Well, it's a nice thing to
No, that looks very nice. Thank you very much.
So thank you so much again.